Hello everyone, I'm Wei Chen, come from Beijing University of Posts and Telecommunications. This work detects the blockchain-based Ponzi scheme, in particular for Ethereum smart contract, and we call it ponzitract for short. Let's start for what is Ponzi scheme. Its root comes back to Charles Ponzi, who promised the investor a high yield return. He can continue the scheme by using part of the new investment to reward earlier investor. In return, the rewarded investor will help scheme attract new investors. However, there are no any actual business or profits generated. The return can only come from the new victims. Thus, when there's no enough new investors, Ponzi scheme will crash. Ponzi scheme has a pyramid-shaped money flow. Usually, the initiator is in the top of the pyramid. If the return is too good to be true, it probably is a Ponzi scheme. There's growing accidental evidence that this scam has emerged in the blockchain ecosystem. In the blockchain, each block connects to the previous one via a hash string of its content. Thus, the blockchain is unique since the subsequence of blocks cannot be modified. Smart contract is the outcome of the blockchain-based Ponzi scheme. The initiator of Ponzi scheme takes advantage of smart contract to treat victims. Firstly, no one can track the identity, so the initiator can stay anonymous. Secondly, no one can stop the execution of smart contracts. Thus, money extracted from the Ponzi scheme do not need to be disclosed. At last, no one can deny the transaction, as the victim's money cannot be found back. Based on the existing study, we found the 4 kinds of the most popular Ponzi schemes, including handover scheme, chain scheme, tree scheme, and withdrawal scheme. Here are some state-of-the-art work. In 2050, the researchers presented the first empirical study of Bitcoin-based scam. As for mathematical tools, we found that all existing efforts are taking advantage of machine learning techniques. Transaction ML relies on transaction behavior of smart contract to perform detection, and the optical ML take the optical extracted from the smart contract particle as feature to train a classifier. The basic idea is that the optical frequency distribution should differ between Ponzi and non-Ponzi smart contract. Note that this classification is follow the extracted feature that this model used. However, there are some limitations for them. For transaction ML, it has poor scalability because it requires a lot of transactions to learn. Thus, only the popular Ponzi tree that can be identified. As for optical ML, it lacks interpretability and it is prone to evasion technicals. We found that these types of Ponzi trees have some features about the semantic information. Here is an example of tree scheme. In this function, enter message.value indicates the investment. Message.sender indicates the investor. In the purple block, the investor registers his information into the tree-shaped data structure. And in the while loop, the smart contract reverses the further node of the investor. The semantic information can help us to identify the Ponzi tree with more interpretability and high accuracy. And we want to propose a semantic-based detector based on these patterns. To this end, there are two challenges need to be solved. The first challenge is that we have to perform internal calls. There are three threads of calls can invoke another smart contract, including call, static call, and dedicated call. To solve this, we built cross-contract paths and then performed the symbolic execution to recover the returned value. The second challenge is that we had to pass storage variable based on the low-level information. Smart contract can save persistent data in storage, which is a fixed size vector. Each element or slot is 256 bits and can be stored or loaded by a slot position denoted as sigma. A slot variable is a part of the slot, which is located by the offset and the size of the variable, denoted as epsilon and omicron respectively. Considering the storage variable in nice sense, we need to recover semantic for its corresponding bytecode. This variable owner is the first 116 bits of the first slot in the storage. Parsing the slot variable is very important for our study, because all users' data is stored in the storage first. So the Ponzi chain can select a participant to reward. To solve this, we express each storage variable with three solver. And the syntax in the Fig A can help us to understand the actual structure of the storage variable. And we can find the semantic information. For example, after the symbolic execution, engine executes those opcode in the green block. The semantic of the variable owner is generated in this syntax, which can be expressed as a true theta. The theta is 4, 0, and 160. Here's the overall architecture of the SADPonzi. You can find there are three main components, including path builder, X engine, and Ponzi pattern detector. The path builder generates visible paths to the imported opcodes, and the X engine constructs the symbolic constraints along the path. These two components are used to solve challenges 1. The Ponzi pattern detector is used to solve challenge 2. We proposed two algorithms here. The first algorithm passes the AST of the storage variable and outputs the theta, indicating its address structure based on the syntax in Figure 9b. The second algorithm recognizes the types of the variable by passing the ST of the slot position or sigma. In this paper, we believe a Ponzi tree contains a redistribution scenario to divide new investments among its previous participants, and thus the money flow is pyramid shape. Here is the summary of the semantic information. In the investing action, a player invokes a transaction to invest Ether, which is the official cryptocurrency in Ethereum, and the Ponzi chain stores user information in the storage. Secondly, in the rewarding action, the Ponzi tree pays a bonus for the participant players. At last, in the PMA distribution strategy, Ponzi tree selects a participant to reward. Here are some details of how we find those actions. For investing action, it will register the investor's information in the storage. Therefore, we should find the optical store that satisfy the following patterns. The first store should say the address of the investor, which is a 116-bit vector. The second store should say the investment, which is an expression depending on the message dot value. The rewarding action is achieved by the optical core. The recipient address should be read from the user information structure rather than in the investing action. Here are some details of how we match the pyramid manifold. The detail of these rules are in our paper. You can check our paper for more description. Let's see the experimental results. The first evaluation is about the effectiveness. After setting the timer as 20 minutes and the maximum core divs as 30 layouts, we can we run the SADPonzi on the variable benchmark, including 1,395 samples. Note that the 133 Ponzi trade are remarked from the existing benchmark. We remove the duplicate contract and non-Ponzi smart contract. For the fair comparison, we re-imply 2 ML baselines. And here's the result. The result of the transaction ML is in line with the evaluation in previous work, because ML performs better than the one reported in their paper. You can find SADPonzi outperforms existing state-of-the-art machine learning approaches. SADPonzi, perceiving full semantic information of contract code, achieves a good balance between accuracy and scalability. In RQ2, we evaluate the robustness of SADPonzi against evaluation technical. The evaluation are generated by BM, which is a source code level obfuscation tool developed for Solidity. We obfuscate optical in three ways, including layout obfuscation, data flow obfuscation, control obfuscation. We can find SADPonzi is resilient to 4 types of obfuscation strategies that are commonly used today. However, the performance of the optical ML decreased sharply when facing obfuscate and evasion smart contract. Surprisingly, when just after being recompiled, most of the Ponzi trains can bypass the detection of optical ML. Next, we measure the prevalence of Ponzi trade. In the large-scale dataset, we find 616 unique contracts, and they can be extended to 835 because some of them have the same bytecode, and over half of them are trend scheme. We also measure the creation type and the creator of the Ponzi trace. We can find we identify 835 Ponzi scheme created by 444 accounts in total. These Ponzi trains were created all the time within the span of 5 years, beginning in April 2016 and October 2018. This suggests that Ponzi schemes are prevalent in the ecosystem. Last, we measure the impact of the Ponzi trade. The number of transactions is huge. There are over 5.98 million transaction records and 3.3 million incoming transactions. The number of victims and the amount of money is also huge. 17,000 victims have sent over 100,000 Ether. Our observation suggests the great impact upon the chains. It reveals urgency to identify the great blockchain Ponzi scheme. In conclusion, we propose a semantic-aware approach for Ponzi trace detection. We developed SADPonzi. Second, we developed a SADPonzi working on Ethereum smart contract protocol. SADPonzi can perform all the ML-based lines. At last, we applied SADPonzi to all 3.4 million smart contracts on Ethereum, and we identified 835 Ponzi trades involving over $17 million US. That's all. Thank you.